If we're going to understand how neurons generate the electrical signals that make the brain work, those electrical signals that lead to how we think, how we feel, move, how we sense our environment, we need to delve a little bit further into the properties of the neuronal membrane. So let's take another look at this lipid bilayer that we discussed earlier. We have this hydrophilic end here, which, as you know, has a strong affinity for water. So it turns towards both the extracellular space, which is an aqueous space, and the intracellular fluid. Attached to these hydrophilic heads are hydrophobic tails. You see here and here, here and here. Hydrophobic molecules turn away from water, and so you see these tails turning inward toward each other, forming a rather impenetrable layer in between the two hydrophilic layers. We also have in this structure those integral proteins that I mentioned earlier that go from one side of the bilayer to the other. And we have extrinsic proteins, which are proteins that lay on one side or the other, but don't go all the way through. Now this gorgeous illustration nicely depicts what's going on at the level of the bilayer, but it's also a really good demonstration on why we can't have a meaningful conversation at a carnival. And we can discuss this later on when we're talking about attention and learning and memory on why people like me have difficulty with this. I'm learning a lesson here, and I've got pink arrows going one way and blue going another. I've got all kinds of black arrows and positive signs and minus signs, and I can't really focus on what the message is. And when you add in really dense text like this, it's like leaving a party really glad that you showed up, but not being able to remember anybody's name. So I'm going to go back to my rather primitive drawings to try to flesh out what's really going on here. You have your lipid bilayer, which is, let me get to my pointer here, which is here. You have the hydrophilic domain here, pointing outwards, and you have the hydrophobic domain here, pointing inward. So let's just agree, for all intents and purposes, that this is the extracellular domain here, and this is the intracellular domain here. And now we'll get rid of those so that we can have more space and get down to business. We have a lot of ions floating around in this space. We have sodium, potassium, chloride, which is a negative charge, and we have negatively charged proteins in the intracellular space. We also have many ion channels, like this one, throughout the membrane that allow ions to pass through the cell membrane. And while the membrane is relatively impermeable to sodium, meaning sodium has a difficult time getting through, the membrane is relatively permeable to potassium, meaning potassium can flow through the membrane either to the outside or back to the inside. These ion channels are called passive or non-gated ion channels. And the fact that the membrane is relatively impermeable to sodium means that there's a higher concentration of sodium on the outside and a lower concentration of sodium on the inside. We also have gated ion channels here, which require some sort of stimulus to open them and allow the ions in. We have embedded in the membrane a structure known as the sodium-potassium pump. This is what we call an active transporter that uses the molecule ATP. If you remember, ATP provides energy for the cell. Uses the energy from ATP to move ions into and outside of the cell. And for every molecule of ATP that's converted to ADP, we have 3 molecules of sodium that are moved from the inside to the outside of the cell, and 2 molecules of potassium that are moved from the outside of the cell to the inside of the cell. So what we end up with is a higher concentration of sodium outside of the cell and a higher concentration of potassium inside the cell. Now, as I mentioned earlier, there are these passive ion channels that allow potassium to kind of flow in and outside of the cell. So as the charges build up, potassium wants to flow with the concentration gradient and go outside to equalize the concentration gradient. But I also mentioned that there are negatively charged proteins inside. So as the cell becomes more negative inside, the positive ions on the outside, both sodium and potassium, want to get back in the cell, are drawn back to the negative charge inside the cell. The sodium just can't get back in because it doesn't have passive channels to go back through. The potassium, on the other hand, can flow back through these passive ion channels and go back into the intracellular domain. So we have an excess buildup of sodium outside the cell, meaning excess buildup of positive charge. We have positive charge in the cell, but less so than outside of the cell. So what we end up with is about a, negative 70 millivolt difference between the inside and the outside of the cell. Meaning that the inside of the cell, not that the inside of the cell is negative, but it's negative relative to the outside of the cell, and it's negative relative to the outside of the cell by 70 millivolts. So this difference in charge you have across the membrane is called an electrical gradient. And we also mentioned that there was a chemical gradient that causes potassium to move from the inside of the cell to the outside of the cell to reach equilibrium. So you have 2 forces kind of working against each other. You have the electrical gradient and you have the chemical gradient. So what we end up with is when the force to move potassium with the concentration gradient out of the cell is equivalent to the force used to pull potassium back into the cell to offset the negative charge, we end up with electrochemical equilibrium. Please be aware of a couple things. First of all, even though we've calculated the resting membrane potential here as minus 70 millivolts, negative 70 millivolts, you will also see it noted as a minus 65 millivolts. So both are correct. So let's go back to the slides from the book. You have here what we talked about initially. We're looking at the passive ion channel, and in this case the potassium channel, which allows potassium to move inside and outside of the cell membrane. We have the sodium-potassium pump, which in the presence or conversion of ATP to ADP releases energy, extruding 3 sodium ions from the cell and moving 2 potassium ions into the cell. Again, you have more non-gated potassium channels. So here you see it kind of close up and personal. Again, intracellular fluid, extracellular space, 1, 2, 3 sodium ions, 2 potassium ions. ATP converts to ADP, releases energy, moving 2 potassium ions into the cell and moving 3 sodium ions outside of the cell. So what we see then is a buildup of positive charge on the outside of the cell and less positive charge on the inside of the cell, again making the cell negative 65 to negative 70 millivolts from the inside relative to the outside. One issue that has not been particularly clear in previous classes, and so I'm pointing it out specifically this time, is the difference between sodium-potassium pumps and ion channels such as sodium and potassium channels. Sodium-potassium pumps such as those seen here are not ion channels. They are ion pumps that are enzymes, and they require energy in the form of the conversion of ATP to ADP to move ions in and out of the cell. Conversely, ion channels are membrane spanning proteins comprised of 4 to 6 subunits that allow for the movement of ions across the membrane. These proteins can be passive, which allows for the free flow of certain ions, or they can be gated, meaning they need some type of stimulus to allow for